All set. Our hearing will come to order. I want to welcome everyone to our hearing on biomass for thermal energy and electricity, a research and development portfolio for the future. Before we begin to discuss the topic of today's hearing, I want to particularly recognize some special guests in our subcommittee today. Members of both the Liberian and Haitian parliaments are here as guests of Representative David Price from North Carolina as part of a week-long seminar on committee operations. I understand there are fellow committee chairs here among our guests, and we're very honored that you're here. It's particularly appropriate to have international governments community with us today, as biopower, of course, is a very much linked to the global issues of climate change and energy security. The members of Parliament include the Speaker of the House of the Haitian Chamber of Deputies, the President of the Haitian Senate, the Chair of the Haitian Committee on Justice, and the Chair of the Haitian Committee on the Budget. The Chair of the Liberian Committee on Natural Resources, Energy, and the Environment is also here with us, along with other members of Parliament and dignitaries. Excellencies, thank you all for joining us. We welcome you here. We also know that our committee hearings can go somewhat timely if you have other engagements. We won't take it personally if you have to go to another meeting, but we're very grateful to have your presence here, and we're honored. And did you wish to offer any comments before we start, Bob?
Just also add our welcome on this side. We're very grateful that you're here, and hope that it's a good visit and a productive visit.
Thank you very much. With that, we will proceed with our discussion of today's hearing. We will today examine a number of different technologies utilized to convert biomass feedstocks into biopower and discuss the federal role in development of these technologies. While more widely known as feedstock for liquid transportation fuels, biomass can also be used to generate heat and electricity, a field otherwise known as biopower. Biomass includes, of course, any organic matter that is available on a renewable basis, including agricultural crops, wastes and residues, wood and wood waste and residues, animal waste, municipal waste, and aquatic organism. But, of course, if these things are used for energy, they're not waste after all, are they? They are raw materials for which we can generate power. Biomass feedstocks are vital as the country moves toward a more diverse portfolio of energy sources, especially in the southeast and northwest of the country, where there are significant quantities of these renewable resources. For example, a 2005 report published by the Washington State Department of Ecology and Washington State University found that our state, my own, has the potential for annual production of over 1,769 megawatts of electrical power from biomass. This is roughly 50% of Washington State's annual residential electrical consumption. Furthermore, in my home district, we have abundant amounts of forest biomass. When this resource is harvested in conjunction with the Sustainable Forest Management Plan, important restoration goals can be achieved, such as wildlife mitigation, watershed protection, wildlife habitat restoration, and reduced insect infestation, and we can generate valuable power as a result as well and reduce our CO2 output. To realize these benefits, new research needs to be funded. Enhanced basic and applied research and commercialization of a diversity of conversion technologies needs to be advanced. In 2002, the Bush administration consolidated liquid transportation fuels, bioproducts, and biopower research efforts across DOE into the biomass program, and since then, the large majority of the research has focused on liquid transportation fuels, primarily ethanol. However, given the decreasing availability of fossil fuel resources and simultaneous increase in demand, along with concerns of lethal overheating of the earth and ocean acidification, a responsible 21st century energy policy will include a renewed commitment to biopower technologies. While the development of liquid transportation fuels from biomass is a critical research area, I am interested in hearing from our witnesses about increasing biopower research efforts in the federal research portfolio and the steps we need to overcome barriers to new biopower technologies. My apologies to the translator with our guests. I speak awfully fast. Good luck. And with that, I'd like to thank this excellent panel of witnesses for appearing before the subcommittee this afternoon. I yield to our distinguished ranking member, Mr. Inglis, for his opening statement.
Thank you, Mr. Chairman, and thank you for holding this hearing today. For the last 10 years or so, we've primarily been looking toward biomass as a replacement for petroleum-based transportation fuels. The result has been a substantial interest in converting food crops to fuel, with smaller emphasis being placed on developing cellulosic ethanol. Environmental and cost concerns are cultivating interest in other types of biomass as a fuel for baseload electricity and thermal power. Some biomass can be and is already being used in conventional generation technology. Paper mills generate power from milling waste, and woody biomass can be mixed with coal and co-fired in modern large-scale power plants. More research and technological innovation can expand the reach of renewable biomass fuels in our energy sector. The subject of today's hearing represents a step in that direction. Developments in renewable natural gas, biorefineries, biomass transportation, and other technologies will help increase the efficiency of biomass energy, and the diversity of organic materials can be used for energy generation. I'm looking forward to hearing about the state of the industry today and where we should direct federal research and development resources to overcome remaining technological hurdles. I also want to admit to a parochial interest in biopower. Two South Carolina universities, including Furman in the upstate and USC, have launched already bioenergy pilot projects. Our robust forest industry stands to gain jobs and a larger market. As we'll hear from Mr. James, biomass energy is already creating jobs back home. Thank you, Mr. Chairman, for holding this hearing. I look forward to hearing from the witnesses and yield back the balance of my time.
If there are other members who wish to submit additional opening statements, your statements will be added to the record at this point. At this point, it's my pleasure to introduce our witnesses at this time. Dr. Don J. Stevens is a Senior Program Manager at Pacific Northwest National Laboratory, PNNL. Mr. Scott M. Clara is the Director of the Strategic Center for Coal at DOE's National Energy Technology Laboratory. Mr. Eric Spomer? Eric Spomer is the President of Catalyst Renewables Corporation. Dr. Robert Burns is Professor of Agricultural and Biosystems Engineering at Iowa State University. And I'll again yield to my friend and ranking member, Mr. Inglis, to introduce our last witness.
Thank you, Mr. Chairman, for the opportunity to introduce Mr. Joseph James, who is a terrific example of alternative energy industry that's creating new jobs in South Carolina. Mr. James has over 35 years of experience in economic development devoted to achieving equity for disadvantaged people and communities. Since 2004, his career has taken on a new focus, aiming to create jobs and revitalize rural African-American communities in South Carolina through opportunities in the emerging biomass and bioenergy fields. In recognition of his pioneering work, he was awarded the 2008 Purpose Prize. He's also a bioenergy entrepreneur. He's a founding member and vice president of the board of South Carolina Biomass Council and a member of the Southeast Agricultural Forest Energy Resources Alliance. He's the president of Agritech Producers, which is developing and commercializing biomass technology in South Carolina through partnerships with North Carolina State University and Kuster Zima Corporation in Spartanburg. Looking forward to hearing from him about this innovative torrefaction technology that Agritech Producers is bringing to the market. And we thank him for being here.
Thank you, Mr. Inglis. As obvious, we not only have professional interests as members and chair and ranking member of this committee, we have personal interests as we represent districts with great potential. Our colleague, Dr. Bartlett, as you may discover when he offers his questions, is one of the real leaders in walking the talk of renewable energy. He is probably the lowest carbon footprint of any member of Congress in his residence, and I admire that greatly. So he brings great expertise. With that, we'll begin. As the witnesses know, we have 5 minutes for testimony, followed by questions from the panel. We invite you to begin. We'll begin now with Dr. Stevens. Thanks again to all of you for your presence.
Thank you very much, Mr. Chairman and the members of the committee. I very much appreciate this opportunity to be here today at a time when our nation's moving forward with a sense of purpose and urgency toward a more sustainable energy future. And biomass is certainly part of that future. As a nation, we have approximately 1.3 billion tons potentially available on an annual basis for a variety of energy purposes. As you indicated, those resources come from woody biomass, from agricultural residues, from dedicated energy crops, and others, all of which vary significantly on a regional basis. We can use that for a variety of purposes, biofuels, or for the topic of today, biopower. Several technology options exist to convert biomass to biopower, including direct combustion, gasification, and pyrolysis, which I'm talking about today. So what's pyrolysis and why is it important? Well, biomass pyrolysis is simply the process of heating biomass in the absence of air to produce a combination of liquids, solids, and gaseous products. And we can control the relative amounts of those by selecting the process conditions accordingly. Today I'll focus on so-called fast pyrolysis, which produces a liquid product referred to as bio-oil. That bio-oil has several important characteristics that are beneficial for power generation. Most importantly, the bio-oil can be used in high-efficiency electric generation systems, systems that can't directly use solid biomass. With stabilization and upgrading, the bio-oil can be used in industrial turbines, combined cycle systems, or potentially solid oxide fuel cells. These have electric generation efficiencies of 30 to 40 or more % compared to a simple wood-fired boiler system with efficiencies of 15 to 25%. And since we have a finite amount of biomass in our nation, it's important to use that efficiently to meet our national energy needs. Both nationally and internationally at present, there's significant interest in using pyrolysis. Technologies to produce bio-oil are in the near commercial stage of development, and there are several large-scale development units with capacities ranging from about 5 to about 200 tons per day in operation to produce bio-oil on a demonstration basis. However, at present, no fully integrated commercial bio-oil to energy facilities exist. The primary technical barrier at this time is the need for stabilization and upgrading. Stabilization is necessary so that bio-oil can be stored and used for periods of several months. And additional upgrading is needed to meet equipment specifications for high technology conversion systems. The upgrading, among other things, chemically neutralizes the bio-oil and removes mineral salts. There are quite a few national and international research programs currently focused on removing these technical barriers for the utilization of biomass. Pacific Northwest National Lab, for example, is working with many partners, including industry, Department of Energy, USDA, other national labs, and universities to improve bio-oil stabilization and upgrading. And we're also looking at the use of catalysts to improve the initial quality of the bio-oil as it's formed to reduce the need for downstream stabilization and upgrading. In addition, we're working in collaboration with a range of international groups to understand just how much stabilization and upgrading is needed for various applications for bio-oil. PNNL leads the International Energy Agency's pyrolysis task, and we're also working with groups in Canada, Finland, and Asia on other pyrolysis issues. As a result of this work, we're making significant progress in overcoming the technical barriers for using the bio-oil. In summary, I would like to conclude by noting that pyrolysis offers flexible options to meet our national and regional energy needs. The bio-oil gives us the opportunity to more efficiently produce electricity, and that national and international programs are assisting industry by resolving the existing technical barriers. Thank you.
Mr. Chairman and distinguished members of the subcommittee, thank you very much for the opportunity to appear before you today and discuss some things that Agritech Producers LLC is doing. I want to give a special thanks to Congressman Inglis for his interest in our work. It turns out that our manufacturing partner is located in his district, even though our company is not within his district, but we greatly appreciate his interest and his support. I'd like to state a problem. Cellulosic material, wood and agricultural material, is not an easy substance to work with. It's generally about 50% moisture, and particularly in the case of wood, it's bulky, it's of relatively low energy value, and the economics of getting it from the place of harvest to the place where it's actually going to be used as a fuel or energy sometimes means that we leave a lot of that material, of that 1 billion that was referred to earlier, remains in place where it might have been growing. So a solution is required to that problem, a solution that removes as much of the water as possible, that densifies the energy content of the material, that also may change its physical characteristics in such a way that utilities can co-fire it and grind it very easily and mix it with coal, as well as other users, and other logistical approaches such as densification, crushing the material into briquettes or pellets, will help facilitate its usability. And of course, there's a challenge in developing the appropriate supply chains to get material from the point of where it's been grown and harvested to the point where it could be used. And I do want to emphasize there's a real need for a focus on solid fuels in addition to liquid fuels. So I appreciate your comments earlier, Mr. Chairman. About 3 years ago, we got focused on something called torrefaction. Torrefaction is essentially a process, again, it's a mild form of pyrolysis actually, which drives off the water. And in the case of the innovations that North Carolina State University has developed, we're able to capture some of the off gases and use those as process heat. So the process that we operate is about 80%, uses 80% green fuel, if you will, and very little fossil fuel and outside energy. I won't go into any more details in that. My written testimony has quite a bit about the process. But the key thing is that it creates fuels from either wood or from agricultural material that can be used cost effectively. And when I say cost effectively, we're talking about producing material that may range in the $80 to $100 a ton range and may have BTU counts or energy content in the 11,000 BTU range, which is very comparable to coal. And the pricing of that is also comparable to coal in pricing. Our company has been very fortunate to have received a variety of federal and state support in our efforts to commercialize this very exciting technology. One of our affiliates years back was fortunate to get a grant from the U.S. Forest Service's Woody Biomass Utilization Program. And our assignment was to work in the National Forest in South Carolina and try to create new markets for the biomass that results when the forest does its thinnings to reduce the hazard of fire and also to improve forest health. We quickly learned what I've just described, that if you're close to the customer, it's easy to take that material and ship it to the customer for their use. If you're more than 30, 40, 50 miles away, it is almost impossible to make the economics work. That's when we went looking for a solution to that problem and discovered the torrefaction process at NC State. We've also been fortunate to have received funding from the U.S. Forest Service's Wood Education Resource Center, and we're using those resources to help us investigate the differences between torrefying hardwoods and torrefying softwoods. As you might guess, different materials have different characteristics, so there's a need for research to fine-tune or possibly make different kinds of equipment to handle different kinds of material. Mr. Chairman, we're very fortunate as well recently to have gotten a grant from the Department of Energy under their SBIR STTR program, which is allowing us to look at the feasibility of developing mobile torrefaction units, which would allow us to go from farm to farm or forest logging deck to logging deck, be able to collect more material from dispersed places and put that into the channel of material that can be used. I do have some suggestions about some additional federal support that would be helpful to us. One is increasing the availability of financing for small companies. We're very fortunate at the moment that we don't need financing to advance our manufacturing of torrefaction equipment. However, as we get into and spend a little bit of our time on the processing side, the credit crunch that our country is suffering, particularly for small companies, is creating some challenges that we're going to need some help with. In addition, we have some very exciting IP. Our intellectual property is much in demand around the world. And we're getting inquiries from China, India, Russia, and other places which may or may not properly respect IP. We'd like to be part of the global solution for renewable energy, but as a small company, we're very nervous about sharing our IP in certain places abroad. Any help that the federal government, either legislatively or in negotiations, bilateral or otherwise, would be extremely helpful to us as well. And then lastly, we believe that in addition to industrial scale activity, where hundreds and thousands of tons of material are processed by large fixed units and large facilities, we think there's tremendous opportunity for forest-reliant communities and rural communities to use our technology on a community scale, if you will, to work in their forests, to work with their farmers, improve forest health, but also generate new revenues and new jobs in those communities. DOE and USDA have funded large-scale research, or research into large-scale biomass supply and biomass value chain operations, we would suggest that in addition to that, in order for us to have, and others, to have impact on rural communities, that we should also be looking at the community scale or micro scale as well, and we'd be glad to participate in that. In your own state, Mr. Chairman, we've had a number of forest communities contact us looking for ways to add value to the materials that they have available to them. We would love to be able to provide demonstration units to them so that they might accomplish that particular mission. In summary, we're very excited to be with you today. We think there's some great opportunities to move forward, and we look forward to working with the committee. Thank you.
Excellent testimony. Thank you. Ms. Clara.
Thank you, Mr. Chairman and members of the subcommittee. Appreciate this opportunity to provide testimony on behalf of the United States Department of Energy's Clean Coal Research Program, particularly those activities related to co-feeding biomass materials with coal that reduce the life cycle carbon intensity of electric power generation in large industrial processes. The Clean Coal Research Program, which is administered by the Department's Office of Fossil Energy and implemented by the National Energy Technology Laboratory, is designed to remove environmental concerns over the future use of coal by developing a portfolio of innovative clean coal technologies. In partnership with the private sector, efforts are focused on maximizing efficiency and environmental performance while minimizing the cost of these new technologies. In recent years, the Clean Coal Research Program has been structured to focus on advanced coal technologies with integrated carbon capture and storage. Co-feeding biomass with coal to current and future power plants is a logical part of this strategy. The coal and biomass co-feeding option, when integrated in an advanced energy system with carbon capture and storage, can provide electric power on a life cycle basis with near zero greenhouse gas emissions. Biomass can be co-fed to nearly all coal-based processes, including pulverized coal combustion, advanced oxygen-based combustion plants, and advanced gasification-based plants. When combined with pre- or post-combustion carbon capture technologies, co-feeding biomass offers a very sound strategy to reduce the carbon intensity of these energy systems. Coal biomass systems could become part of an early compliance strategy, particularly in existing power plants. Coal biomass systems can benefit from the economies of scale offered by large coal-based energy systems. Large biomass-only plants are often constrained by low biomass energy density, feedstock water content, feedstock collection and preparation, and local regional feedstock availability. Biomass can be used more effectively as a co-feed in large central coal plants to realize the benefits of the economies of scale. Coal can also serve to offset the seasonal and variable nature of the supply and availability of biomass feedstocks. Considerable experience exists with a number of biomass to power generation facilities that have been constructed and operating, particularly in Europe. The International Energy Agency's Bioenergy Task 32 has compiled a very extensive database to provide a nice overview of this experience. It reports that over the past 5 to 10 years, there has been remarkable rapid progress in the development of co-firing. Several plants have been retrofitted for demonstration purposes, while another number of new plants are already being designed for involving biomass co-utilization with fossil fuels. The majority of these plants are equipped with pulverized coal boilers, which is the standard state-of-the-art technology. Tests have been performed with virtually every commercially significant fuel type. For example, lignite coal, subbituminous coal, bituminous coal, and opportunity fuels such as petroleum coke. And with every major category of biomass, herbaceous and woody fuel types generated as residue and energy crops. Over 40 plants in the U.S. have co-fired coal and biomass over a period of several years. Operations have ranged from several hours of operation to several years, with 5 plants operating continuously for testing purposes, either on wood or switchgrass, and 1 plant operating commercially over the past 2 years on a mixture of coal and wood. Research efforts are currently focused on biomass preparation and pretreatment requirements, feeding coal biomass mixtures into high-pressure gasifiers at commercial conditions, and characterizing the composition of the resultant stream to determine impacts on downstream components. Biological capture of CO2 through algae cultivation is another CO2 reduction strategy that is gaining attention as a possible means for greenhouse gas reductions from these fossil fuel plants. Algae, the fastest growing plants on Earth, can double their size as frequently as every 2 hours while consuming CO2. Algae can be grown in regions such as desert conditions as not to compete with farmlands and forests, and they do not require fresh water to grow. While it is recognized that the greenhouse gases stored by algae will ultimately be reduced to the atmosphere, there is a net carbon offset by effectively using more of the carbon contained in the fuel to produce energy. In conclusion, to establish a new and widely deployed industry based on growing, harvesting, and processing large quantities of biomass fuel on a regular basis, there are some key issues that are needed to address, many of which you're hearing with the other speakers. The single most important issue, we believe, is how much biomass can sustainably be made available to be economically and reliably support a power industrial facility. This factor alone, biomass availability, will in turn dictate the scale of plant or plants in a particular region. Also, experience dictates that the energy crop must not be competitive with the food chain, so land use and crop choices need to be carefully designed and managed. There are a number of technical challenges as well to using biomass in future and current plants relative to things like the biomass feeding, slagging, fouling, and corrosion of downstream processes and components. This completes my statement, and I look forward to the discussion period. Thank you.
Thank you, Mr. Clare. Mr. Spomer.
Thank you, Mr. Chairman, and distinguished subcommittee members. I appreciate this opportunity to share Catalyst Renewable's operational lessons learned and insights on this important topic. I ask that my detailed written testimony be included in the record, as I intend to share only a few key points. Catalyst was a successful green, renewable, and sustainable energy company before being green was so popular. Our biomass experience originates with the Lionsdale plant in Lyons Falls, New York. We purchased this 19-megawatt combined heat and power facility in 2003. At that time, the plant was in distress. But after significant capital investment and reestablishment of trust and confidence with the local forest community, we've been able to help Lionsdale return to viability. Catalyst developed and deployed an approved sustainable forestry management plan in conjunction with its renewable energy credit from the New York State Renewable Portfolio Standard. Today, the Lionsdale wood basket is considered the healthiest forest in New York State. Wood from the forest and purpose-grown woody biomass energy crops offer a significant renewable and environmentally acceptable alternative to fossil-based energy supplies. The United States biopower effort is being led by renewable energy generation innovators like Catalyst, and our strategies can be applied to all our U.S. forests. Woody biomass holds significant revitalization potential for rural economies of our forest and farm communities. Woody biomass is CO2 neutral. Woody biomass is sustainable and enhances forest health. So why does woody biomass, around for eons, merit your attention and inclusion in a research and development portfolio for the future? First, wood wins in every environmental, economic, and effectiveness category. Using woody biomass offers a clear national security advantage from using clean, renewable, homegrown fuel for baseload thermal energy and electricity. Woody biomass has a proven, reliable national logistics handling system, but biomass is not just wood. Today, we have no integrated biomass handling system for the efficient and effective inclusion of crop residues and livestock nutrients. So our first research and development suggestion is the design, development, and operational test and evaluation of regional logistics systems, including integration of rail transport and integrated staging areas for woody biomass, crop residues, and nutrient feedstocks. Integrated handling systems must be designed and tested to be commercially and operationally effective and suitable with a minimum of handling touches as industry develops new facilities. A concerted effort to advance commingled biomass supplies would enhance resource use, reduce costs, expand biomass availability for renewable thermal energy and electricity. We suggest multiple regional demonstrations suited to regional feedstocks are reasonable and prudent. Second, Catalyst is constantly seeking cleaner, more reliable production of renewable baseload heat and power. Our foremost concerns are efficiency, environmental suitability, and elimination of greenhouse gas emissions. Presently, our already permitted 37-megawatt Onondaga Renewables plant under development in Gettys, New York, will be the cleanest woody biomass generating facility in North America. These bragging rights do not come cheap. We're commissioning a bubbling fluidized bed boiler. BFB technology is widely recognized as the most efficient combustion conversion device for biomass residues. However, BFB boilers come with a significant associated energy penalty, pressurized airflow, Large quantities of air are required to counterbalance the mass of the boiler bed and propel the mass into a fluidized state, and this results in a 6% penalty on efficiency. In case of Onondaga, that's 21,000 megawatt hours a year. Next, environmentally CO2 neutral woody biomass is also virtually sulfur-free, and our systems can already effectively eliminate particulate matter, leaving emissions of oxides of nitrogen, NOx, the most important remaining consideration. Today we use catalytic reduction systems, including selective catalytic reduction and regenerative selective catalytic reduction. Fresh catalytic units are capable of continuously reducing NOx by more than 98%. At Onondaga, the catalyst will operate at high conversion efficiency for about 10,000 hours, but then it must be replaced and disposed of. Presently, NOx reduction catalysts cannot be regenerated. Finally, maintaining optimum chemical reaction temperatures in catalytic reduction units operated for the elimination of NOx and the elimination of use of fossil fuels as reheat or energy source is essential. Presently, oil or natural gas is burned and to maintain flue gas temperatures to effect rapid and high NOx conversion. For a modern biomass conversion plant, the heat input approaches 10% of the total biomass value. That's 3.7 megawatts of capacity at Onondaga. To summarize, we most strongly suggest specific congressional direction to U.S. DOE and funded research and development authorizations for appropriations to design, test, and deploy integrated biomass logistics systems, to research, develop, and test equipments to eliminate parasitic power loss in bubbling fluidized bed biomass boilers, to research, develop, test, and deploy catalytic units that have extended operational lives and that can be regenerated in place, and to research, develop, test, and deploy energy improvements able to eliminate the need for auxiliary fossil fuel usage in RSCR and SCR NOx control devices. Mr. Chairman and distinguished subcommittee members, thank you for the opportunity to provide this testimony.
I'd like to thank the committee for the opportunity to provide information today. It's a privilege to be invited. I was specifically asked to speak about research and development needs regarding the anaerobic digestion of animal manures to produce energy via biogas. Anaerobic digestion is a conversion of manure into biogas, which contains primarily methane, through a process that's without air. It's a process that's been around for years, we've used a long time, and have a relatively good handle on. The biogas that's derived from animal manures can be used as a renewable energy source in various ways. It can be directly utilized on farm for heat or other uses. It can be directly combusted in boilers to produce hot water. It can be cleaned and conditioned, what we call upgraded, and can be injected into the natural gas pipeline. It can be used to fuel engine generator or microturbines for electricity generation, or used as a fuel source for Stirling engine cycles, fuel cells, and some other options. In addition to producing renewable energy, the anaerobic digestion of animal manures also provides some environmental options. It reduces odors, which in a farm setting is a very important situation. It reduces organic material, potentially reduces pathogens, and generates marketable carbon credits for sale through the reduction of the base greenhouse gas emissions from those systems. The manure from dairy, swine, beef feedlot, and layer systems has been successfully digested in the U.S. and abroad, and some types of manure systems are more easily to install digester systems on than others. But if we took a look at the manure from all four of these species that I just mentioned, layers, beef feedlots, dairies, and swine systems, and were to anaerobically digest all of that manure in the U.S. to produce electricity, we could generate over 20 billion kilowatt hours, which would represent about 0.5% of the total U.S. electricity generation in 2008, or about 17% of the non-hydroelectric renewable energy provision in this country. But we have to recognize that we can't necessarily digest all of that manure. We can't get 100% market penetration. The U.S. EPA AgStar program has done some very good reports that have looked at what systems are feasible. Specifically in the dairy and swine industry, they believe that some of the larger systems are more feasible, and if we take that market share that they believe would be good candidates for digestion, it still represents about 6.3 billion kilowatt hours per year generated. The implementation of digesters in the U.S. has been very limited, however. Currently, we have 135 operational manure digesters in this country. If we contrast that to the two leading countries in the world, China and Germany, China currently has 16,000 manure anaerobic digesters that are medium and large scale, similar to our confined animal feeding operation systems, concentrated animal feeding operations, I should say. Germany has approximately 5,000 systems that are manure-based or manure and silage-based. The AD technology is proven, but what we've seen is that the energy production costs in this country are too high to compete in the competitive market. From a standpoint of going back on the grid, typically you're going to see wholesale rate in the U.S., which is going to average around 3%, varies by location of the country. Germany's currently receiving 33 U.S. cents per kilowatt hour for that similar energy, and in China, 9 to 10 cents per kilowatt hour. The research and development needs then that I see are those that could reduce the cost of energy derived from manure anaerobic digestion systems so we can compete in the current energy market. And specifically, some examples of these R&D gaps that I'd like to share with the group. First is the low-cost biograding options. We have tried and true biogas upgrading systems, but currently the reported cost to upgrade biogas is equal to or greater than the current cost to purchase natural gas. So it makes it not economically feasible to pursue that option. The development of lower cost systems, especially that could be applied on farm and smaller systems, would be very useful. The development of additional direct use options would also be handy. As I mentioned, because the cost for biogas upgrading is so high, if we could skip the upgrade costs and directly use unconditioned biogas, especially on the farm, it would give us a much more economical opportunity to do a cost avoidance situation. This is very basic research, but it's very practical in nature. It's something that would provide a lot of forward traction if we could come up with those systems. Next, the development of anaerobic digestion systems that are compatible with swine deep pit finish operations. Most of the pigs in this country, the majority, are finished in the Midwestern United States, and the majority of those finished systems utilize what's called a deep pit system, manure stored directly under the animals. Those systems are not directly compatible with anaerobic digestion systems, and the development of a system that it would allow the adaptation without large cost, again, would bring that market sector into the game. The adaptation development of high solids digestion systems to manure systems. There's been high solids or dry digestion systems in the municipal world for some time. To move those systems into manure would also provide benefits. Finally, the development of advanced lower cost NOx controls for biogas combustion and generation systems. In some parts of the U.S., specifically in California, NOx limits are lower than we can currently achieve that are being written into permits with a lot of the technology that's out there from a cost-effective standpoint and has limited some implementation. I'd like to conclude by saying the number of manure digesters in the U.S. is increasing. I think this is primarily due to the fact that we see increasing grant support at the federal and state level to build digesters, so we're going to continue to see these systems come online. We're not cost competitive in the energy market right now. And this topic touches energy, environment, and agriculture, and I think it presents an excellent opportunity for DOE, EPA, and USDA to work synergistically to help answer some of these gaps. Thank you very much.
Thank you, Dr. Burns. An outstanding series of information from all of you. Thank you very much, and I will recognize myself for 5 minutes to ask questions, and will be followed by my colleagues here. Thanks again to our honored guests. We appreciate your presence and wish you a good day and enjoyable visit. Thank you very much. Dr. Burns, I have a question that I've got a lot of questions for all of you, but let me just start with this one since you just spoke. It's my understanding that methane is a more potent greenhouse gas by quite a significant factor relative to CO2. In the energy bill, I don't know the answer to this, and maybe you don't either, but I'm going to ask. In the energy bill that's been kicked around in the House and what's working in the Senate, does reduction of methane through the kind of process you've described, do you get a greater credit for that than you would if you were reducing CO2 by volume? I don't know that that's the case, but it seems like it ought to be. You need to hit your mic again or move it. Is it lit up? There you go. There you go.
Okay. Yes, sir. Methane is recognized to be 21 to 23 times more potent than CO2, depending upon which protocol and time scale. Now, if I can rephrase the question, are you asking is the combustion of methane, obviously when we combust methane, we also generate some CO2 in that process. And if I understand you correctly, you're asking if we receive a net gain from the combustion of methane as compared to the CO2 that's emitted from the process.
That's part of the question, and then the other question would be this. If we're not in some way using the methane to generate energy, presumably some of that's just being released into the atmosphere. So do you get, under any of the energy bills that are moving, or do you think you should get credit for reducing the methane that's going into the atmosphere through your kind of processes?
Yes, well, and I think the answer is yes, you should get credit, but it has to be recognized that the credit increment is tied to what was the existing system, i.e., if there had not been a digester at this location, how much methane would be generated.
Right.
Because once the anaerobic digestion process is put in, we're going to greatly increase the methane production. So it's that differential click between the two that should be credited.
Gotcha. Very, very good point. One of the things that strikes me as I listen to the testimony of all of you, really, is that we've got this remarkable resource that can be used in a number of ways, and I really appreciate that. I think our staff's done an outstanding job of giving us diverse perspectives on ways things can be used. But as I look at the biomass program in DOE, and maybe I'm wrong and maybe someone can correct me, or if not, help us figure out what we ought to do. But as I look at the biomass program and biopower, really, like we're talking about today, it's really been neglected. It's mostly been fuels. It's mostly been, and mostly, frankly, ethanol. I mean, we've just put so much effort into that, and it seems to me at the expense of much of what you're doing. And so what I'd like to ask your comments, some of you've all actually given excellent suggestions for things DOE could conceivably do better. It doesn't seem like it's being done now. It's almost solely focused on ethanol. What do you have some comments on how, if this committee or this Congress were to direct DOE and say, you know, we want you to give more attention to biopower in any of the forums you all have talked about, how would that best be accomplished in your interaction with DOE? And some of you work for some of the labs that get funding for DOE. I don't want to put you on a difficult spot there, but from your professional expertise, how could we best make sure that we're broadening the portfolio of possible uses of biomass? And I'll just open that up to whomever wants to take a stab. Mr. Spomer, you look ready to go, so fire away.
Well, I think the first thing that generally exists today is there's a real bias against things that burn. And in whatever form, whether it's gasification or direct combustion, ultimately there is combustion of wood. If we can get past that bias and start to focus on the fact that, you know, according to USDA, from the forest, there's 386 million bone-dry tons a year from the forest alone. When you add all these other factors, you start to get into the 1.2 billion tons per year of biomass. We're talking about eliminating so many, whether it's biofuels or biopower. That would be a huge portion of our national need for power and for fuel. So first we've got to get the recognition that this is good for the forest. The methane question is an excellent one. If this stuff lies and rots in the forest floor, or whether it's ag waste that's lying in the ditch, it's going to convert to 50% methane, 50% CO2. By combusting it, we may be carbon neutral, but we're significantly greenhouse gas positive. The key thing is to use technology and advances in technology and support advances in technology to improve the efficiency of the conversion so we can compete economically.
And as a businessman, I don't want to put words in your mouth, but from what I'm hearing, it sounds like, would it be fair to say that the bulk of the research that's been coming out of DOE in terms of how to deal with biomass as an energy source has not been particularly beneficial to the kind of utilization that you do in your industry?
Almost none.
Okay, so and here's an industry that's using wood products constructively and has revitalized the rural economy. And Mr. James, if you wish to comment on that, please.
Thank you, Mr. Chairman. It might be instructive for the committee, or the subcommittee, to ask DOE to confirm or correct my understanding, and this is from hearing other scientists, that the combustion of biomass is a more efficient conversion of that material into energy than using it to make liquid fuels. Now, I'm not one to suggest we should not make liquid fuels with that material, but we should also be striving for, where we can, maximum utilization and maximum benefit. The other thing, Mr. Chairman, I would suggest that some investigation might be worthy. We're very fortunate to have a technology that's in demand internationally. And I can tell you that the Europeans, and particularly the British here lately, because they've developed some new incentives to use dedicated biomass, if you will, are scouring around the U.S. locking up our biomass in long-term contracts. Now, I don't want to hurt our business opportunities, but as a citizen, I am concerned that there could be a point in the future where we've developed our technologies and we've committed ourselves with the appropriate climate legislation, and we find out that our feedstocks are being exported in other places. I would urge that the subcommittee might ask for some research in that particular area.
Outstanding points, and you said it more delicately than I might, but one of the sad things about, I think, the ethanol emphasis has been that my understanding of the research on that is our net energy output is negative on that after a whole lot of work and investment. I mean, with corn-based ethanol at any rate, not to mention all the food impacts and the fertilizer in the water. I'm particularly intrigued also, Mr. James, by this issue of on-site processing of materials. Particularly, I've got timber communities now that are 20, 25 or more % unemployment. They've just been devastated. And the idea that when you go out there with your skidders and everything else, all the logging equipment that you could take out along as part of the contract, as part of the bid, take out equipment to process wood fuels in some fashion makes an awful lot of sense to me, especially with the economic implications and the energy implications. So I applaud you for that. Anyone else want to talk about this issue of DOE and ways they could maybe diversify the portfolio in a different way?
Just one thing I'd like to give DOE some credit for. They've supported our effort at developing plantation fuel, purpose-grown biomass in New York. We've done some interesting work with the State University of New York, Environmental Science and Forestry College on purpose-grown, dedicated woody biomass. I think that in addition to the existing portfolio that was described, could really make a difference. It takes fallow farmland, otherwise not useful. This is not a competitor with food. It's an opportunity for people to get a revenue stream, and that is particularly good because it acts as a carbon sink in addition to being carbon neutral on the generating side.
Great. Thank you. I recognize Mr. Inglis for 5 minutes. I apologize to my colleagues. I went over a little bit.
Thank you, Mr. Chairman. So show and tell, Mr. James, do you have any of the product with you? I was hoping so, because I saw it in Spartanburg, and I thought that will you get it, Katrina? Maybe have you seen it?
Is this product placement?
Yeah, it is. Have you seen what it looks like?
No. Has anybody got a match?
A pipe might be appropriate if you could light it in a pipe, and it is maybe not. Maybe
we don't
not.
deal with that in this committee.
So anyway, it is really interesting.
Sometimes people on this committee, I think they've been smoking something, so we're going to leave that.
Yeah. So it's something my colleagues would be interested in seeing it, because I got to see it in Spartanburg. It's a very interesting product. You can see how it could be fed immediately into mixed with the coal, and right. That's what we're looking at here.
Yeah, yes, Congressman, I've given you 2 samples. One is torrefied wood chips, and the other is semi-torrefied, or a mixture of torrefied.
You haven't mixed up Dr. Burns' substance with this. No. Before I pass this down, I want to.
Yeah. Although we are exploring whether the process can be helpful there.
Yeah, sure.
But you also have some torrefied switchgrass condensed into a pellet. Excuse me, a briquette. So you've got 2 forms of samples there.
Thank you.
Yeah.
So this is efficient to burn as an energy source?
It's extremely efficient, much more efficient than untreated wood or cellulosic material.
And would you burn this around? I'm sorry, I'm jumping into your time.
No, it's all right. You can smell it. It smells just sort of like charcoal or something like that. It's been
Pass this down to Roscoe. He'll be wanting some of this on his farm.
Yeah, there you go. So, you can, by looking at it, you can see how easily it can be co-fed with coal, I guess, because it has sort of look and feel of coal, pulverized coal. It just has less energy density, I guess, in it, because it's less dense stuff. But and also, I've got one of these brochures. I'll show it to the chairman of what it looks like out in the field, the machine out in the field, so that you can basically at the location get rid of some of the water and thereby reduce the transportation costs as you move it on to where it's going to be burned, right?
Yes, the picture you're referring to is the prototype on campus at North Carolina State University. And we are developing, with the help of Custer's Zima, your constituent company in your district, larger units that are fixed units that will be placed close to forested areas or agricultural areas. But thanks to DOE support, we're also looking at developing mobile units, which will be on wheels, we hope, and be able to actually go from logging deck to logging deck, maybe from community to community, in order to process material as close to the point of harvest as possible.
Yeah, that's very interesting.
Mr. Chairman, you and your committee members or subcommittee members are certainly welcome to come and take a look at the prototype at some point in time if you choose to do so. We'd be glad to make arrangements for you.
Do you have any wipes for everybody up here now that's got it all over their hands? The chairman was just wiping his hands all over my papers. I want you to know, I want for the record to show. Anyhow, so I guess I asked for it. So that's very, very helpful. Dr. Burns, the BMW in Spartanburg, South Carolina gets more than 50% of its power from a trash dump. Takes the methane, runs it through a 10-mile pipeline, and powers north of 50% of the power needs of the plant. And the interesting thing about that, there are a number of wonderful things about it, but one of them is that they've speculated in the future, perhaps rather than the NIMBY principle, we might actually be saying, here, put your trash right here in my industrial development. I want a big trash dump right here. So instead of a 10-mile pipeline, we have a half-a-mile pipeline to a bunch of industrial facilities that are using. Similar problem, I guess, for siting hog farms and things like that. If they become, though, an energy producer, then it's less hard to site those, I suppose, right?
There's certainly an economy of scale that's associated with energy production through anaerobic digestion. Landfill biogas production systems are typically much larger in terms of the generating capacity than manure systems would be. They also, my understanding is landfill systems are currently, electricity generated from those systems is probably done so at a cost that's a third or so the cost of what we're currently seeing as generation costs from manure digestion systems. Again, they're larger systems, typically 3 to 4 megawatt generating capacity, and they're very predictable systems. With a landfill operation, the material's there, it's entombed, and there's a very predictable life expectancy. You're going to be able to draw a curve that says what's the gas yield going to be. It's going to exponentially come up, it's going to level off, it's going to decay, so you know that yield. And there's other factors that make manure digestion a little tougher. I mean, animals are not coming in and out of the landfill. There's not potential changes in your biomass generation capacity in that landfill because the gas yield from the landfills occur generally after they're closed, and then you yield that gas toward energy. So they've been very successful, but it is a model that can be looked at. But there are some differences, and primarily scale, I think, would be the one that would be different from what we see in ag systems with manure.
Thank you. Thank you, Mr. Chairman.
Thank you. Dr. Bartlett.
Thank you. You mentioned that you get more energy from burning this than if you burned wood. But unless we're going to suspend the law of thermodynamics, you won't get more energy from it than you would have gotten if you burned that wood, because you have some energy invested in creating this product. So really, you're trading convenience for energy, because you're going to get less energy out of your wood eventually if you go through this process and then burn it than you would have gotten if you burned it initially. So you're trading for energy for convenience here, are you not?
Congressman, of course you're correct. However, the systems, boilers and otherwise, that burn material burn more efficiently with higher BTU and less moist material. There's a lot of energy if you were to burn green wood. You've got to use a lot of energy to evaporate the water off of that, and you're sacrificing some of the efficiency of your boiler.
So that helps offset your loss here.
Exactly.
Let me ask you a question about forest health. Absent fires, how does removing biomass from forests make them healthier? If we look at a tropical rainforest, if you remove the biomass, you've removed essentially all of the nutrients because they're all in this cycle of life. That has to be somewhat true in our temperate forest, although nowhere near to the extent of the tropical rainforest. I'm having trouble understanding how removing biomass, absent fires, how removing biomass makes the forest healthier.
Well, I can use the example of upstate New York and really the whole northeastern mixed northern hardwood forests. Absent an active, typically what happens in New York, for example, absent a low-grade biomass market, loggers, there's active logging going on up there. They're taking the maple, the cherry, the best wood, and with no market for anything else, they take that out, turn it into furniture, tabletops, and they leave the stuff that you really don't want. Diseased trees, unmerchantable timber, sometimes non-indigenous species, and then they also leave the junk on the floor. And there's what happens in the area around Sarah Lionsdale plant is that there's active forest thinning because there's a market for the low-grade material. When pulp and paper was active, there was a market for that low-grade material. Pulp industry has basically dried up in the north, and absent a market for that, you've got a changing nature of the native forest in New York and in Maine and in other places, more so in New York. And those forests tend to be less healthy. And
by less healthy, you mean that they don't have the kind of trees growing there that you would like to have growing. So when you take the trash trees out as biomass, that permits the maples and cherries and so forth to be more competitive.
And also, thinning the forest allows new growth. In a mono-aged forest where you've got a big canopy and you're not getting new growth, you're not as efficient at consuming CO2. A forest fire is nature's way of fixing that problem. It's not a big problem in the Northeast where it's particularly damp. It's worse in my home state of Colorado where the whole forest can go up in a hurry. But being able to thin the forest and allow new growth, diverse growth, is good. The Audubon Society tells us it's good for habitat, and the Department of Environmental Conservation says it's critical for forest health in New York.
Yeah, that helps me understand what you mean by forest health. Doesn't mean you're growing more forest. It means you're growing the kind of forest you would like to grow. I have a question for the second round, and let me just introduce it now. And I have a huge concern for sustainability. Even with no-till farming, for every bushel of corn we grow in Iowa, 3 bushels of topsoil go down the Mississippi River. And topsoil is topsoil because it has organic material in it. We can rape our soils for a few years, and then we will not have the quality of soils we have. We're fighting very hard today to maintain the fertility of our soils. I'm having trouble understanding how we can take very much biomass off our soils and still maintain that that fertility of the soils. But let's come back for a second round to a discussion of this, because I think that experiments in sustainability are the most needed experiments in this field. Thank you, Mr. Chairman.
Thank you, Dr. Brown. I'm going to go ahead and let you follow up on that if you like, because I went over a little bit, as did Mr. Inglis, and I think it's an important line of questioning. So if you're interested, let's follow up on that.
Congressman, if I could respond to your earlier question about forest health. The natural course is for a forest to have fires every several years, which thins out the underbrush. That's the naturally occurring thing.
You're from what state?
I'm from South Carolina.
Okay, that's different than up here. I cannot remember a forest fire up here. It just doesn't happen in our temperate forests, at least none I'm familiar with. Once in a while you have a little litter, on a little dry litter burn, but a real forest fire, we just don't have them. Do we in New England and so forth? I never heard of a forest fire here. It's really different in your pine forest down there and in the West. We don't have them here.
Yeah, my point is to go on to forest health issues. To the extent there's a lot of underbrush and small diameter trees that are crowded against each other, the rapidity with which disease and infestation spreads in the forest is accelerated. So being able to mechanically thin those, since in most forests, we live and we run highways through and we do other things that don't allow prescribed burns to take place. Mechanical thinning is what is happening to the extent there's budget for it. For example, the Forest Service has limited budget, and one of the reasons that they've developed the Woody Biomass Utilization Program was to try to generate a cash stream off of that biomass that would allow them to treat additional acreage in the forest. The other thing I would say is that the process that we have, the living parts of the tree, which are the bark and the leaves, tend to turn into a fine powder, whereas the corpus of the tree turns, you feed chips in, you get chips out. That fine powder tends to have more minerals in it, and we are looking to see whether that can be a biochar or soil application material that could go back into the forest or back on the farm to enhance soil health.
Do other panelists want to address the broader issue of soil quality and the loss thereof in regard to biomass? Dr. Burns?
Yes, sir. I think it's an excellent comment, and I'd just like to comment on when we look at manure anaerobic digestion to point out that those manures will still be land applied as fertilizers. Digestion, it's important to understand, is a nutrient neutral process. The amount of nutrients removed through the anaerobic digestion process for the obligate requirement of the microbes is very, very small. So that those macronutrients are going to be utilized by crops, the NP and the K, it's still going to be there, and farmers that utilize anaerobic digesters are still going to have the same land base for their nutrient management plan, and that manure is still going to go to the field. It is true, however, that it will go to the field with less carbon content than it contained prior to digestion. For beef and dairy systems, we can expect to see 30 to 40% of that organic carbon being converted over to methane and CO2 in the process, and for swine and layers, we're more in the 60 to 70% range. But those nutrients from a fertility standpoint will still be there, and the benefits of the fiber and a lot of that carbon is still going to be there from building soil tilth. So in that system, we're still going to see manure go to the ground as a fertilizer and be utilized that way.
If manure is spread on the field and you go through sheet composting, there's little or no methane produced by that?
In a composting process,
if it's sheet compost, you spread the manure on the field so that there's no anaerobic activity going on. It's very thin. Then you shouldn't get methane, should you?
no, sir. If we keep the system aerobic in nature, we will not generate methane. It will go through aerobic respiration. It will generate CO2. There will still be carbon loss there, and also, unfortunately, with that aerobic process, we're probably going to lose nitrogen out of the system as gaseous ammonia.
You have to incorporate it in the soil to avoid that.
Incorporation of solid manures is recommended to avoid that gaseous ammonia loss. Yes, sir.
Thank you, Dr. Bartlett. Thank you. Important line of questioning, and I think especially regarding what we've seen with ethanol, which you've talked about with great eloquence in the past in this committee. Continuing on the theme I began earlier, it seems apparent that in a number of areas of additional research and government activity, whether it's intellectual property or targeted research on catalysts and a host of areas where we could be doing things, if DOE were to give more attention to biopower broadly, what, from the gentleman's perspective, what office at DOE would be technically equipped to do that? Where would we best go within DOE to make this happen? Mr. James, and then Dr. Stevens.
Mr. Chairman, I'll try to take a stab at that. The answer to the question is I'm not exactly sure. However, the Office of Biomass certainly comes to mind. If I could also go back to an earlier point that you made, we participated with others in our region in one of the last solicitations for a biomass supply chain. And as I recall, the language in the solicitation did not exclude making solid fuels, but there may have been a bias towards liquid fuels. I think your staff might wish to analyze the awards that came out of that solicitation, it may make sense for whatever part of DOE is going to take on this assignment to have a very specific solicitation for solid fuels or some other types of activity that supports some of the testimony that you've heard today, so there's not an ambiguity, and then I guess some opportunity for, I don't want to use the word bias, but some opportunity for not fully exploring that opportunity.
And to follow up, Mr. James, obviously you're in the industry that would deal more with the solid rather than the liquid. Would there be a counter argument that would say, well, the reason they were biased, if there was bias, or the reason they favored, let's not deal with predilections, but maybe they just made an empirical scientific judgment that there's more bang for the buck, so to speak, or better return on investment in liquid fuels. Is that the case, or do you think it was more? Again, I'm not trying to put you on the spot, but the question for me is, we should be looking at all our options, but we have to look critically at those options. So,
I think we should look at all options, and we support all options. However, the understanding that I have from the scientists that I'm talking to suggests that direct combustion, whether treated or untreated, of biomass gets more. You end up with more energy on a net basis than you would by converting it into a liquid fuel.
Partly because of Dr. Bartlett's repeated observation of the second law of thermodynamics.
I'm sure he's right again on that, sir.
Thank you. So your point would be, whichever branch of DOE is focused on this, we want it to be a focus that's not just in name only, and we're going to go right back to the liquid result.
And the other thing I would say, Mr. Chairman, that the electric utilities and other coal users are great collaborators, and we've had good luck in working with a variety of utilities, so there's an opportunity to leverage some of the users, including coal suppliers, if you will, into this process, because we all need to figure out how do we work together, how do we use existing distribution and supply chains that are already in place in order to make a system work. So I think if a solicitation could be a little more specific on, in our case, on solid fuels, and encourage collaboration between users and suppliers and other members of that value and supply chain, that we could come up with a very robust solution.
Yeah, it'll be my intention following this hearing to actually inquire precisely of these kind of issues of DOE in writing. We'll drop them a note. Dr. Stevens, I want to applaud PNNL for its work on forest products, obviously, given our region, and PNNL has really been a pioneer. What insights can you offer on this question?
Well, I'm not in the position to recommend where you put your money, but I would simply comment that Office of Biomass Program has had active biopower programs several years ago. And several of the people who worked on those then are still there. The expertise is resident, and the capability exists there today for applications-oriented work. And of course, Office of Science is capable of doing very basic work as well. As a recommendation, it would be very useful to bring together the two to solve both the very fundamental problems and the applications problems in a meaningful way.
That's very, very useful. Maybe we should move the first presidential caucus to a timber state, and we would have a different focus on the products. Anyone else wish to comment on this? Mr. Inglis?
Thank you, Mr. Chairman. Dr. Burns, I'm very interested in what you're talking about and how it may apply to human waste as well as animal waste. As in Mumbai a while ago, and we were traveling through the city at 2 or 3 in the morning, and I really thought if we struck a match, we might have exploded. We were told, I don't know if it's correct, but we were told it's because they discharged the effluent into the bay at that time of day. So it's 2 or 3 in the morning, and it was just an amazing amount of methane aroma. I haven't grown up at the coast and known what marsh grass is like, or marsh gas is like. So it really struck me that a country like that has so many people and has to come up with some way of coping with that waste problem. If you can turn waste into something good, it sure is a win-win proposition. And actually, while there, we visited a place where they're doing that. They're taking food waste from a dormitory and turning it into methane that then powers the kitchens. And I asked them about actually not the scalability, it's the opposite of scalability, keeping it small enough that you could actually do a neighborhood that way. And they said that is the challenge, is you don't want to, in the case of such a system, you don't want to build it so large because you lose some of the benefits. If you can do it much more locally, you have this great benefit of being able to have a relatively small system that takes a great deal of, takes the waste and then turns it into something useful. Is that something that, as we develop things on the farm, is that a possibility of moving into the city with those kind of lessons learned on the farm?
I think there's great examples around the world of where that's already been done, and I think whether you're going to see that implemented or not is going to depend on where you are in the world, i.e., what's the relative cost of energy. For example, the largest number of manure digesters by far are in the class of what we call domestic digesters, where human excrement, night soil, is mixed with household waste and some animal manure. Specifically, right now there's over 37 million of these household-type digesters in China, and they've been growing significantly because the central government of the People's Republic of China has put a great amount of funding into supporting their construction. I've done work with these systems outside of Tianjin in some watershed projects where they're using them to try to reduce pathogens and so forth. But what you see is it's very quickly adopted system, and that the biogas is generated is used for heat, for light in these systems. India has 4 million of these systems. Nepal has 140,000. You see them in locations, again, where the relative cost of energy, if you were to look at the cost of say, purchasing propane or natural gas in those communities versus the cost of going out and picking up wood to build a fire in the corner of your home, those costs are such that it makes a lot of sense to generate biogas and use it. If we look at the relative cost of energy in this country, you know, you don't see those systems adopted because energy from a relative cost from our income is so low that we're going to purchase it rather than pick up wood to cook. There are, though, examples of a lot of biogas being generated from municipal wastewater treatment plants in this country. It's very common. It's been done for years. It's very successful. Those facilities, however, are typically aerobic treatment plants because recall that we mentioned anaerobic digestion is nutrient neutral. So we'll go through the tertiary treatment process and use an aerobic step where we'll biologically remove nutrients, and it may also be with some combinations of some chemical steps as well. But then the solids that are generated off that other primary clarifiers are typically digested anaerobically, and that biogas yield will then be converted through either IC engines or microturbines into electricity production. So we do see it come from that standpoint.
Anybody else want to add anything to that? Or if not, thank you, Mr. Chairman.
Dr. Bartlett.
Methane is the coal miner's black damp. Is that true? The explosive gas in coal mines is methane, is it not? Which is odorless, isn't it? So the odor you get from the swamp is not the methane. It's something that goes along with the methane. Our irrational exuberance over bioenergy has resulted in two bubbles which have burst. The first was the hydrogen bubble, and nobody talks about hydrogen anymore because I think they finally figured out that hydrogen is not an energy source. You will always get less energy out of the hydrogen than it took to make the hydrogen. The second bubble that broke was the corn ethanol bubble, and I and one of my staff people did some early back-of-the-envelope calculations and reached essentially the same conclusions that the National Academy of Sciences reached. They said that if we turned all of our corn into ethanol, every bit of it, and discounted for fossil fuel input, it would displace 2.4% of our gasoline. They said you could save more gas than that by tuning up your car and putting air in the tires. They further said that if we took all of our soybeans and converted them into soy diesel, a more efficient process, by the way, than corn ethanol, that this would displace 2.9% of our diesel. Now, most of our arable land is, our farmland is planted to corn and soybeans. And so just as an old dirt farmer, being very practical, when I note that if we took all of our corn and converted it to ethanol, discounting for fossil fuel input, you'd displace 2.4% of our gasoline. And if you did the same thing for all of our soybeans, for soy diesel, you displace 2.9% of our diesel. And noting that corn and soybeans are grown on almost all of our land that's good enough to grow row crops on, I'm wondering sustainably how much we should really expect to get from our lands that aren't good enough to grow either of these crops on. I just think that the third bubble that's going to break is the cellulosic ethanol bubble. I think we'll get something there. I think that we'll get nothing like the potential that many people feel are there. Am I wrong?
This is a topic I know something about, and you've asked a number of questions in there. First, on the purpose-grown portion of it, let's use the state of New York, for example. We're looking at getting 5 bone-dry tons per acre on about up to an available 2 million acres of fallow farmland that's perfect for fast-growing woody biomass willow. And that's a coppice crop. We don't till the soil. You'll go through 21 years of life before you have to replace it, harvesting every 3 years. That 5 tons per acre, let's assume we just get 1 million of it planted, is 600 million potentially, based on a process that we're working on, is roughly 600 million gallons a year of petroleum products, not ethanol. The conversion, as I used to say, if it was easy to turn wood into alcohol, some guy in Tennessee would have figured out how to do it a long time ago. The fact is, though, it's not a stretch to turn it into hydrocarbons, and it's being done. It can be done.
Now, what about sustainability, though?
Well, the sustainability side of it is your harvest plan. Are you taking biomass, which by definition in a forest sense is the waste, you never go down and cut a tree down just for biomass in the Northeast. They're going to go in and do their normal logging, thinning process. And
but if you leave that on the those trimmings in the forest, it then contributes to the humus in the forest and therefore the nutrients, which helps additional trees grow. At least to some extent, our forests have to be a bit like tropical rainforest. When you remove the tropical rainforest, you have laterite soils that bake as hard as a brick, and you have essentially no good agricultural land.
Okay, but the worst thing you can do to the forest is put a farm on it. The best thing you can do for a forest is keep it thin, because, for example, in New York, it takes up to 60 years to grow a harvestable tree. You've got 60 years of leaf shed from that tree that's nutrientizing, what is the word for that? Putting nutrients back into the soil. When you take down a typical northern hardwood, up to 50% of that tree is not going to be turned into furniture. That remaining top and limb is going to rot in the form that you would see it in the forest, and it's not going to necessarily turn into nutrients. It's going to be turning into methane and CO2. That's the stuff we clean up. Those leaves that shed every year are going back to put nutrients back into the soil. So from a sustainability perspective, it's at least demonstrated in New York specifically that thinning the forest properly increases the total rate of growth of that forest, and therefore the CO2 intake of that forest. You're giving it more room to move. You're allowing younger trees to grow. So from a sustainability perspective, at least, and we're not the experts, we rely on experts who've told us this, that it is truly sustainable and truly good for the health of the forest long term. So if you just assume that on a national basis, assume that's true on a national basis, we're talking about half of the hydrocarbon fuel use in this country could come from sustainable forest biomass.
Mr. Chairman, I'm still skeptical when I look at what we could get from all of our arable land, and we expect to get many times that from this land that's not good enough to grow either corn or soybeans on. I still remain skeptical of what the real sustainability is going to be. Even though those limbs and tops rot and the CO2 and methane goes off, you've still got humus there. That's what holds water. That's what holds nutrients in the forest. So you still have something very valuable that's left after that. Thank you, Mr. Chairman.
Thank you, Dr. Bartlett. And I can speak just briefly about the North. I'll get to you in just a sec, Dr. Burns. In the Northwest, one of the challenges we have is we've got literally millions of acres of disease, and this is really true in the Rockies, of diseased trees, which are tinder dry and ready to go up in smoke. Now, admittedly, not the entire tree burns unless it's a really bad fire. And what's happening in the Northwest is we're actually thinning some of those out for forest health in two ways. If forests are overgrown, that increases the fire risk. But also, if you've got insect-infested trees, you need to get those out. Here's the sad part from a global overheating perspective. We're actually taking that wood out, stacking it up, and burning it. Now, if you care about CO2, which I know you do, and so what the paradox for me is we're actually spending good money for the sake of forest health to get this stuff out, but we actually are not using it for energy. And sadly, the initial draft of the energy bill that passed the House expressly prohibited the use of forest products from federal lands to count as biomass. And not only did it prohibit that, it so severely restricted private lands that became impractical. And then the downwaste stream. So let's say you process the byproducts into pulp and paper, and you get black liquor out as a byproduct. The only way you could count black liquor, according to the initial bill, as a renewable fuel source was if every shred of fiber upstream came from a renewable source, as defined by this. It was a ludicrous approach, and actually I got that fixed in the energy bill. So myself and a coalition of others, but it was maddening to see a bill that was supposedly designed to diversify our energy portfolio and reduce greenhouse gases, basically giving no credit for using greenhouse gases for fuel and leaving it instead on the ground to rot or burn up. So your point is absolutely well taken, and I think it absolutely does apply if we were to just say we're going to grow huge forests and we're going to cut them down and never replenish that soil. I think you do have some adverse impacts. But when we're taking byproducts out from the normal harvest process or from dead and diseased trees, I think we can use it actually pretty productively. Not that it's a panacea, as some looked at I think, ethanol. Dr. Burns, you had a comment.
Yes, Mr. Chairman. I wondered if it were possible to circle back to your question on what office in DOE would be best equipped to provide broader assistance in the R&D area. I didn't.
Not just possible, desirable.
Okay, thank you, sir. Perhaps the Energy Efficiency and Renewable Energy Office might be the correct office to look at some of this. They've been involved in fuel cell work and advanced conversion to electricity work, and I believe might be the appropriate people to take a look at some of the R&D needs that were identified earlier in the hearing.
Share with me your insights on why that would be superior. I don't have a dog in the fight. I'm just to say the biomass activity.
I don't have experience with the biomass office, and I'm just simply familiar that the renewables office has been doing some work that fits closer to this category or closely with this category. I don't know compared to the biomass office.
Okay. We've gone a long time today. Did you have another follow-up question, Dr. Bartlett, Mr. Inglis? I'm not going to ask you to do this on the record, but actually on the record if you want to, but I'm not going to ask today. But if any of you want to comment at some point about how DOE can be more responsive, it's not just about what entity is there, but you all have given us, I mean, very good suggestions for everything ranging from intellectual property rights, as I mentioned earlier, catalysts, et cetera, to technologies, to logistical flow of materials. I don't know, I'm not experienced enough or knowledgeable enough to know, you talked about DOE drops down requests for proposals or grant opportunities, et cetera. To what extent is there a bottom-up process? In other words, where you all could talk, actually I'm going to ask you to answer that. Where you folks are people in the industry, not just you here, but others who may be in the audience or doing other things, can say to DOA, hey, here's what we really need. Not you telling us what you think we need, but this is what we need. Can you conduct some research or create proposals? What mechanisms exist, or have you been able to, both pro and con, if there are both? And then we'll finish up if my colleagues will indulge that question, please.
Mr. Chairman, I'm not aware of any specific mechanism at the moment. We do have relationships with USDA, and they have created conferences and other kinds of get-togethers that allow us to have some dialogue with them. I remember doing a webinar with USDA staff where several dozen of them were on the line with us talking about torfaction. Thank you for having the hearing. It turns out that some DOE folks that I've been trying to talk with for the last month or so are here, and we're going to get together and do some chatting after this meeting. So
We'll bring donuts to the next one of these, and we'll really get some.
but I think there needs to be more mechanisms that allow us to get together and have some dialogue, and I'm sure the agency will do that. I do want to compliment the Secretary and the energy and that he's brought to the agency. I see a lot of difference in the agency now, and we're looking forward to finding ways to collaborate with them. Thank you.
Great. Anyone else wish to comment on that? If not, I want to bring the hearing to a close. I want to thank our witnesses for testifying before the subcommittee. I want to thank particularly my colleagues for their insightful and informative questions and comments. The record will remain open for 2 weeks for additional statements for the members and for answers to any follow-up questions the subcommittee may ask of the witnesses. Witnesses are excused with our gratitude, and the hearing now stands adjourned. Thank you all very much, and thanks to the guests in the audience as well.